All right, let's jump right in. Today, we're going on a kind of epic journey. It's a detective story that's been unfolding for 2,500 years, all to answer one of the biggest questions you could possibly ask. We're going on the quest for the atom. And this whole thing, it all starts with a single, simple question.
I mean, really think about that for a second. The screen you're looking at, the air you're breathing, you yourself. What is the absolute fundamental stuff that makes it all up? If you could just keep cutting something in half over and over again, what's the smallest possible piece you'd eventually get to? This very question has hooked thinkers for thousands of years.
So, our story doesn't kick off in some modern lab with a bunch of shiny equipment. No, we've got to go way back, thousands of years ago, into the minds of philosophers who were just trying to figure out the world using nothing but pure logic and reason.
And what's so fascinating is that this idea of a final, uncuttable particle, it didn't just pop up in one place. Around 500 BC in India, and then just a little later in ancient Greece, you had thinkers who, completely on their own, came to a very, very similar conclusion. But for centuries, that's all it was, just a really powerful idea. So on one side of the globe, you had Maharshi Kanad, who called this ultimate particle Parmanu. And on the other, you had Democritus, who called his atoms, which literally means uncuttable. The core idea was exactly the same. There has to be a basic building block for everything. But here's the crucial part. This was all just philosophy. There was no way to prove any of it.
Okay, so let's hit the fast forward button a couple of thousand years. We're landing in the 18th century, and the game is changing. Philosophy is making way for actual experiments. Scientists aren't just asking what if anymore. They're asking what happens when. And they started digging up some really strange, really specific clues.
Our first major clue comes from a guy named Antoine Lavoisier. He was doing these super careful experiments, weighing everything, and I mean everything, before and after a chemical reaction. He just wanted to know, does stuff just vanish into thin air or pop out of nowhere when things change? And the answer he found? A huge, resounding no. And that led to this simple but incredibly powerful rule, the law of conservation of mass. If you start a reaction with 10 grams of stuff, you're going to end up with exactly 10 grams of stuff. Nothing gets lost, nothing gets gained. But why? That was the big mystery.
The second clue came from another scientist, Joseph Proust. He noticed something really interesting about chemical compounds, things like water or ammonia. It seemed like they were always made according to a super strict recipe.
Just take water, for instance. It doesn't matter if you get it from your kitchen tap or from a melting glacier. If you break it down, the mass of hydrogen compared to the mass of oxygen is always in a fixed ratio of 1:8. Always. So now we have these two big puzzle pieces, just sitting on the table, waiting for someone to come along and see how they fit together. So we've got these two really important but totally unexplained laws. And this brings us to the man who finally put it all together. The guy who dusted off a 2,500-year-old idea and used it to build the foundation of all modern chemistry.
Meet John Dalton. His story is pretty amazing. He came from a poor family, was already a teacher by the time he was 12. He didn't have a fancy lab or anything like that. All he had was a brilliant mind and those two mysterious laws. And he was about to come up with an explanation that would change everything.
Dalton's brilliant insight, his aha moment, was to bring back that ancient idea of atoms. He proposed that if everything was actually made of these tiny, indestructible little balls, it would perfectly explain everything Lavoisier and Proust were seeing in their labs.
And this is the beautiful part, how elegantly it solved the puzzles. So why can't mass be created or destroyed? Well, because chemical reactions are just atoms rearranging themselves. It's like playing with Legos. You have the same number of bricks before and after you build something new. And why do compounds have those strict recipes? Because they're made by combining atoms in simple whole number ratios. You can't have half an atom, right? It was just a perfect, all-in-one explanation.
So Dalton's theory wasn't just about explaining old laws. It gave us a completely new way to think about the world. But you know how science works. You answer one big question, and a brand new, even tougher one usually pops up. If Dalton was right and atoms of different elements have their own unique masses, how on earth could you possibly weigh one? They're ridiculously small. You can't just pop one on a scale. This was the next huge challenge. Well, the solution scientists came up with was just ingenious. We can get our heads around it with a simple analogy.
Imagine a fruit seller who has no metal weights. So he just decides that one big watermelon is going to be his standard, and he calls it 12 units. He then cuts that watermelon into 12 perfectly equal slices. So now, one slice is his standard 1 unit. He can't tell you how many grams a grape weighs, but he can tell you it weighs, say, half as much as one of his watermelon slices. He's measuring everything relative to his standard.
And that is almost exactly what chemists did. Instead of a watermelon, they picked a specific atom, a carbon-12 atom, to be their standard. They defined one atomic mass unit, or U for short, as exactly 1/12 the mass of that one carbon atom. And just like that, they could start expressing the mass of every other atom relative to this new standard.
So now, with this amazing new tool, relative atomic mass, scientists could finally start to decode the recipes of the universe. They could figure out how the atoms are actually combining to make all the stuff we see around us.
Okay, let's walk through this with our old friend, water, because this is the moment it all clicks together. We know from Proust's law that the mass ratio of hydrogen to oxygen in water is 1 to 8, and we now know their relative atomic masses are 1 and 16. So if you just divide the mass ratio by the atomic mass for each one, you get the numbers 1 and 0.5.
So what's the simplest whole number ratio of 1 to 0.5? It's 2 to 1, which means for every one oxygen atom, there must be 2 hydrogen atoms. And boom, just like that, using the laws and the relative masses, the iconic formula for water, H2O, is revealed. This was absolutely revolutionary. So think about that journey. It started with Maharishi Kanad and Democritus just wondering. It went from a pure idea to a powerful theory that explained experiments, all the way to today, where with our technology, we can literally take pictures of atoms. What you're looking at here isn't a computer model. It's a real image of the surface of silicon. And those little bumps, yeah, those are individual atoms. So, we found the ultimate building blocks. We figured out the instruction manual for how they fit together. This whole journey has given us a brand new language to understand our world, and it leaves us with one last, really inspiring question. Now that we know the rules of the game, what incredible new things are we going to build?